Okay, we're going to check out a different example here. One that hopefully is going to be, I'm going to pause and dim the lights real quick. Sorry about that. It seems like really doesn't like too much light coming in here. I got a window right off to the side. It's brighter as day goes on. So we're going to look at a similar type of example, but we're going to rotate it around the y-axis as opposed to the x-axis. So if we consider this graph, came up with some easier equations this time compared to last time. So we have y equals x, y equals 0, that's going to be the x-axis, and then y is equal to 4. Or x is equal to 4, excuse me. And we're going to revolve that around the y-axis. So, since I do a horizontal revolution, I draw a horizontal rectangle. See that that's going to give us our empty space. That's going to give us our solid space. You see the washer that we have? This is going to be little r, which in this case is y is equal to x. And this is our big washer, or our big radius, which is 4. So if we set up pi times big R squared, we have 16 minus little r squared. And this has thickness of dy, so therefore has to have a y variable. So you can see it's just y equals x. So we could say it's x equals y and insert just y here and square that. dy is our thickness. That is going to be the area, or I'm sorry, the volume of one washer. You want an infinite number of those, so slap on that integral. And we are looking at y values for our integration. So look at your original area, which is this triangle. This triangle is the original area. And we're going to be integrating from our bottom y value to our top y value. So our bottom y value is 0. And our top y value is going to be right at this coordinate right there. That coordinate is 4, 4. And so 4 ends up being our top value. And there we go. So that's a little bit easier, just the nature of the function. So we have pi times 16y minus y cubed over 3, evaluated at 4 and 0. Or pi times 16 times 4 is 64, minus 4 cubed is 64 over 3. And now what we do is we just find common denominators. 64 times 3, 192, minus 64 over 3. And looks like that's going to give me 128. So that's a nice example. Works out pretty slick. Just have a nice triangle shape that you're revolving around. Bounds are easy to find, and the equations are pretty easy to work with. So that only took 4 minutes. So we should be able to get through our second example here without making another video. So this one, we're going to look at example 2. Y is equal to 1 over x and x equal to 2 and y equal to 2 around the y-axis. Okay. All right. First question is, do you remember what 1 over x looks like? It's a reciprocal function. And so it starts up and it heads on down like that. Okay? And then it says x equals 2. So if I go over 1, 2, that line, and then y equals 2, I have 1, 2. And so that's my region. Okay? That's the region I'm looking at. I'm going to take that and revolve it around the y-axis. So I'm going to draw a horizontal rectangle there. As I rotate that guy over, you can see, you'll get a shape like that over on this side. There's your space in the middle. So the space in the middle is empty. The rest of it is full. You get that washer shape. I'm going to draw the washer out here so I can make this a little bit more clear. Obviously, this example is a little bit more complicated than the last one. And I do like to organize my work like that. I really do. I feel like drawing the washer off to the side and then those lines where the bounds are formed is really important. This is just, x is equal to 0. That's what I have for, that line. This mark right here, you look at the inside of the washer. The inside of the washer is formed by y is equal to 1 over x. Okay? And then the outside of the washer is formed by y is equal to, x is equal to 2. So if you want to figure out the distance of the little radius, which is right here, it's just right minus left. If this wasn't x equals 0, if it was something else, they were revolving it around 1, then it would be 1 over x minus 1. But it's just 0, so it's 1 over x minus 0, which is 1 over x. And then the bigger radius is 2 minus 0. Again, if we're revolving it around 1, then the radius would just be 1. So 2 minus 1 would be 1. So in this situation, big R is just 2. So the thickness, as we said from the beginning, is dy. So that means everything must be in terms of y. Right now I have a 1 over x. So I need to change that. So instead of y equals 1 over x, it's x equals something with y. If you look at y over 1 is equal to 1 over x, if I cross multiply, I get xy is equal to 1, and then divide both sides by y, x is equal to 1 over y. So this radius can be changed to, instead of 1 over x, just 1 over y. And that should be enough to really be able to get it to work out for us. Pi times big R squared, which is 4, minus little r squared, and little r squared is going to be 1 over y squared, dy. Now, we don't just want one of those, we want an infinite number of those, so we slap on an integral. We're looking for the y values of our original area, so if you look back at this region right here, this is the region that we're originally working with right there. That's what we want to be able to use to determine our bounds. You're going to see that this top mark here was x is equal to 2, so that's our top. But the bottom happens to be the intersection between y is equal to 1 over x and x is equal to 2. Well, if you plug 2 in for there, you get y is equal to 1/2. So 1/2 is our lower bound. You can see it doesn't go all the way down to 0. Okay, so that's how we set that up. So let's go ahead and find an antiderivative here. Antiderivative of 4 is 4y. Antiderivative of y to the -2 is going to be y to the -1 over -1. It's going to switch that to a positive, so plus a 1 over y, and we evaluate it at 2 and 1/2. Plug in the 2, and we get 8 plus 1/2 minus, plug in a half here, and we get 2 plus, plug in a half here, 1 over a half is 2. So we have pi times, let's see, this ends up being 4. 8 minus 4 is 4 plus a half. So we end up with 8 halves plus 1/2 is 9 halves. Or 9 pi over 2 is our final result. Part of what I love about these problems, and part of the reason why we cover this even at this point, is we decide what material is most important. Because trust me, we're leaving stuff out. You look at the breadth of the material that you're covering, and this is what makes it just so cool. Look at this guy right here, okay? You are using algebra as you're graphing these functions, 1 over x and x equals 2 and y equals 2. You're using system of equations as you solve for the intersection point for the bounds. You're using geometry when you do big R squared minus little r squared. You're doing calculus when you do the integral. You're using differential calculus when we set up the derivative and the antiderivative here. There's just so much going on in terms of your mathematical history. It really pulls all those ideas together. Everything from when you were in 7th grade all the way through till now. It brings a lot of those ideas together, which is why Volumes of Revolution of Solids is a favorite piece for me and a lot of people teaching calculus. So just one video for that part. You should be good to go. Just got 3 problems from one set, 3 problems from the other set. Hopefully that should do you well. Reach out to me and let's sit down and do a video conference if you need help with anything. I would love to be able to help you out. Have a great day, folks. I miss you guys.